We're now going to look shortly at two more versions of the p-chart, the NP chart and the 100p chart. Now remember, for the p-chart, we had the statistic p, which was the proportion defectives in a sample, calculated as d over n, where d is the number of defectives in a sample of size n. Now, this means if p is equal to d over n, then d is equal to p times n, or n times p, as we have written here. So, instead of plotting p, we could plot NP, which is simply the number of defectives found in a sample, and this is called the NP chart. Now, the control limits have to be calculated differently, of course. You can use the same formulas that you've used before. If you remember, this is the same formula, except that for this NP chart, we've multiplied through by n. We've taken our control limits for the p chart, we've multiplied through by n. Now, this could be called a D chart, right? It's called an NP chart, and it means that you are actually plotting the number of defectives. The other thing you can do is to multiply these limits, multiply the limits for the p chart by 100. And then, instead of having the fraction defectives, we've got the percent defectives, or the percent defectives chart. Now let's look at a comparison of all of these. So the p chart, we know, let's say we've got a p chart with sample size there equal to 20. We calculate then our upper control limit, lower center line, and lower control limit for n equals 20. Sample size equals 20, and we have two then other options. We can calculate an NP chart or a 100p chart from exactly the same data. So first thing we do is we have to translate the control limits then. For the NP chart, we multiply through by n. So 0.1 times 20 gives us 2, 0.54 for the center line, and still 0 for the lower control limit. But this time we would plot n times p. And again, n here is equal to 20. And we would have the NP chart. For the 100p chart, we would take our control limits and we would multiply those control limits by 100. So we would end up with 0.1 times 100 for 10 as the upper control limit, 0.027 times 100 is 2.7, and then 0 for our lower control limit, and we plot 100 times p. Now, why would we do this? Well, the advantage of using an NP chart or a 100p chart can be seen. The NP chart avoids calculating p. You're just counting the number of defects and you're plotting them. Don't forget, NP is equal to D. For the 100p chart, the advantage is that we have large numbers compared to these small fractions. You've got in the D chart here, this NP chart, you end up with number of defects that you're plotting, or defectives. This is a whole number. People like to work with whole numbers. For the 100p chart, at least you're still talking about a percent defective, but it's a large number. It's you're, instead of talking about 0.43, you're talking about 43%. So these are all the same. The message here is all these charts are giving you the same information. There's no magic or anything. You're not learning new things, but it depends who you're working with, depends on what's being used in the company. You may decide that a P chart could be more understandable if you plot the NP or a 100p chart. Our last chart that we want to look at is the U chart. And the U chart is a variation of the C chart, which you remember we were counting the number of defects on units as they came through an inspection station. Now, the C chart, and this is important, can only be used if all the units are identical. And here we talk again about this idea of opportunity for defects. The opportunity for a defect must be the same from unit to unit in order to use our C chart. But there could be situations when, for example, an inspection station is receiving units that are similar but not identical. So this could be items of different sizes, like television sets of different sizes, television screens of different sizes. You could have cars with different models, maybe printed circuit boards that have different configurations. So these units are coming in, but you want to use one single chart to control them. And this is where what we use is a U chart. And here we have the statistic U, which is representing the average number of defects per, let's add the word here, standard unit. The average number of defects per standard units. So the way we're going to do this, we're going to define one size as our standard unit. And then the extra work here is that all the other sizes have to be then transformed into a standard unit or a number of standard units. So we're going to be then using different control limits for our U chart, which will depend on an N value. An N here. So first of all, U, our statistic, is going to be equal to the C value, the count of, for one unit, of the defects in that unit divided by N for that unit, where N is the number of standard units in each of the sample units. So it's not the sample size here, it's this transforming factor. A unit is going to be made up of a certain number of standard units, and your control limits then will have to reflect this. So this is very similar to our P chart with varying sample sizes. We're not going to have one constant upper control limit, lower control limit. We're going to have an upper control limit, lower control limit, which depend on the number of standard units in that particular piece. So let's go through an example. And again, this is an example to make you aware of what type of charts are available. You should feel comfortable with C charts and P charts. Here we have a U chart, and here we have a foundry that's producing engine blocks. And sometimes there's holes in the castings that are used. Then you pour the hot metal into the castings, and you need to maybe have someone fill some holes. As long as there's no problem with the structural strength of these castings, you can fill up the holes and still use them. But they want to keep track of the variable number of holes. So, not strictly speaking a defect, but they want to keep in track of this, because if you start seeing the number of holes going out of control, you need to find out in the molding line that's making these castings what's going on. Maybe they've got some problem and the number of holes is increasing, and could lead to structural problems. So they'd like to control the number of holes, but the casting types are different. So here we have 20 samples, 1 to 20, and here's the casting type. And what we've done is we've chosen a standard size. This is block I4, which means inline 4-cylinder is your standard unit. And we've chosen this to represent one standard unit. So N is equal to 1 for the I4. But if you have, for example, a V12, it must be much bigger, they're looking, in this case, at the surface area. The surface area here represents opportunities for defects of the molding process, and this, again, you don't know this, we're telling you this in this example, but this would be something that the quality team would have to decide what makes up a standard unit and why, and how can we then translate all of these other types of casting types into a standard unit represented by I4. And so V12 represents, according to surface area, 3 times an I4. V6 represents 1.5 an I4, and V8 represents 2 I4s. So because these casting size varies, we need to use a U-chart. Now, here we have then the calculation of the statistic U, shown here in this column, where U is going to be equal to the number of holes counted divided by, normalized by this N value. So we have our statistic U. And what we can also calculate then is our U bar, the average U, which is then the sum of the number of holes divided by the sum of our standard sizes that we have, and we get U bar is equal to 4.373. We also have here, which we can also use later, an N bar value, the average number of standard units that we have in our 20 samples is equal to 1.635. Now, as we said before, we're going to be plotting our statistic U. We're going to be plotting this with upper control limits, center line, and lower control limits. Where the center line is going to be equal to our U bar, and these are going to vary depending on the number of standard units in each sample. And this looks like this. So, what we see here is center line here equal to 4.373. Now, as an example, the upper control limit for the 20th sample, so if we did the upper control limit for sample 20, we'd be equal to that 4.373 plus 3 times the square root of 4.373, and the 20th sample had an N equal to 2. And 20 was equal to 2. And so in this case, we get 8.809 as our upper control limit. The lower control limit is actually going to be negative 0.06. So then we round that up to 0. So here we have 8.809 and 0 for our 20th sample. But as before with the p-charts with varying sample size, we end up getting sort of a step functions. Now here in these charts, the LCL is mostly 0, but the UCL you can see is varying. And what we have here is one of our samples, it's actually sample 8, is out of control. For sample 8, this upper control limit was equal to 10.646, and this value is out of control. We don't need to go through this again. Another way of doing this is to calculate for the average N bar. Remember the average N bar here was equal to 1.635. Well, if you plug that into your control limits, you'd end up with the UCL and the LCL with this average N bar equal to just 0 and to the here 0.9279. And in this case, even with the average value, you see that all the points are in control except for this one. So in this example, you get the same values whether you calculate the control limits for every single different sample or if you calculate it for just an average overall. So this ends then our introduction of a few commonly used other control charts. You should familiarize yourself with them and know when they're appropriate, particularly if you're looking at things with different sample sizes and you want to be able to use just one control chart to monitor them. Thank you.